Right, so it's a great pleasure to introduce our next invited speaker of this morning session, Nathan Wilson. He's coming from Technical University of Munich, and he's focused on engineering exotic states in van der Waals, materials controlling electronic and excitonic states, and today he's going to tell us about engineering strongly correlated fermions and bosons into these semiconductors. So with this, Nathan, the floor is yours, and we look forward to your talk.
Thank you very much, and thank you to the organizers for putting together this beautiful conference. We've already heard a lot about many-body physics and quantum physics in condensed matter systems in the last talk. I'm going to talk a bit more about an experiment. In particular, I have two recent results, which are both on the archive and under review, that I'm going to discuss, that have to do with engineering strong correlations between electrons in bilayer electron systems. And what's special about bilayer systems is that the interactions between electrons in the two layers can be fundamentally different from the interactions between electrons in the same layer. And this allows us to create emergent composite bosons and even control the system's quantum geometry just by engineering the bosons and their distribution in real space. So first, let me outline my talk. First, I will discuss why we use 2D semiconductors as a platform for these bilayer electron systems, why they're very well suited to studying many-body physics. Then I'll introduce the first result, where we show that we can build composite bosons out of a bilayer electron system, and then how we implement a lateral superlattice in a bilayer electron system to hopefully induce some strong correlations among the bosons. Okay, so both of these results tie into a very popular topic in quantum matter right now, which is the idea of an on-demand quantum material. And what is that? Well, maybe I'll start with an example of something that's not an on-demand quantum material. Aluminum. So aluminum, you might know, becomes a superconductor at about 1 Kelvin. But you have no way to turn that on and off besides letting thermal fluctuations wash out all the correlation effects. There's no convenient knob that you can use to tune the interactions. So we'd like a quantum material to be programmable. Can you induce quantum effects with a convenient tuning knob? The second aspect of an on-demand quantum material is engineerability. So I know that if I want to build a building that looks like a fish, I can use reinforced concrete, I can use aluminum cladding, and I can build a building in whatever shape I'd like. Is there a similar toolbox for a material platform that allows us to engineer kind of controllable degrees of freedom and engineer correlated phases of matter? And I would argue that one of the best platforms for both of these aspects of on-demand quantum matter are 2D semiconductors, and in particular the transition metal dichalcogenides, TMDs. So these ones in particular, WSE2, WS2, and their cousins are very popular. And something that they all have in common as monolayer materials is that they have very strong Coulomb interactions. And that's because you can imagine that if you put two charges in a thin sheet of material, most of the electric field, which kind of connects the two particles, traverses outside of the thin sheet of material. And this means that you don't have any screening from the bulk of the semiconductor. There is no bulk of the semiconductor. So you have strong Coulomb interactions, and one of the first manifestations of this is that the fundamental excitations, the fundamental electronic excitations of these semiconductors, the excitons are very tightly bound. So in 2D semiconductors, the exciton binding energy is typically on the order of hundreds of millielectron volts, whereas if you consider a bulk semiconductor, that's typically on the order of 1 millielectron volt. So we have a couple orders of magnitude advantage. So indeed, the interactions are very, very strong. Some other useful properties of TMDs for many-body physics. So they have, in the monolayer limit, they have a direct band gap, which is optically active, which means that we can optically excite excitons, which then reside in the conduction and valence bands, the low-energy bands where we expect the electronic correlations to be taking place. So we can optically inject an exciton, we can let it interact with an electronic ground state and then recombine, and we can perform spectroscopy experiments on the ingoing or outgoing light to hopefully deduce some information about the electronic ground state. And then finally, the carriers in TMDs have large effective masses on the order of half a rest mass of an electron, which further promote many-body interactions. Okay, and then as a device platform, 2D materials are very nice because you can simply mechanically stack them into multi-layer structures. And maybe the simplest and most useful example of this is a capacitor, the humble capacitor. So we have a layer of a 2D semiconductor and then a thin dielectric barrier. Usually we use hexagonal boron nitride, and then some kind of a gate electrode. And we apply a bias voltage between the semiconductor and the gate, and we inject charge carriers, electrons, or holes. And we can do this up to a very high density, or 10 to the 13 per square centimeter. And you can already see, if we look at the exciton spectrum, this is a reflection experiment. So we send in white light and we measure the reflected intensity of that white light. We observe different exciton resonances which change depending on whether we inject electrons or holes. So around charge neutrality, when the gate voltage is 0, we have the 1s exciton and the 2s exciton. That's a ground state and excited state, neutral exciton. If we add some holes to the system, we get this positive trion. So it's a 3-body state of a neutral exciton plus 1 hole. And then if we add electrons to the system, we have this zoo of different many-body complexes. We have a couple of negatively charged trion species. We have a hexaton, a 6-body state, an oxyton, an 8-body state. And it turns out you even get up to about 20-body states, 20-body many exciton complexes in monolayer TMDs. This is already a sign, yes, that we have indeed very strong many-body interactions. But these are still just small local complexes. It's a single optical excitation surrounded by a cloud of bound particles. This is not a many-body ground state of all the charges in the system. And it turns out that the kinetic energy of the charges is just a bit too high in a monolayer TMD to get strong correlations between all the electrons. And in order to induce strong correlations, what we need to do is kill that kinetic energy by introducing a lateral superlattice. The way that we do that is with a Moiré pattern. So if I stack 2 layers of a TMD together with a small twist angle, or if there's a small lattice mismatch, if I use 2 different species of TMDs, I form a long-range Moiré pattern, sort of a beat pattern between the 2 lattices. And I have a new unit cell, the Moiré unit cell outlined in green here, and a new Moiré periodicity. And if we look at different locales across the Moiré unit cell, labeled, see these are the high symmetry points, you can see that we realize different stacking orders. So the atoms in each layer line up differently on top of each other. And to first order, what this means is that in some locales where the atoms exactly overlap each other, the layers are pushed a bit farther apart. And in other locales where they can kind of fall into the interstices in the other layer, the layers get a bit closer together. So you have this topographic modulation. But this also modulates the interlayer coupling. So electrons tunnel back and forth between the 2 layers, and the hopping integral is different depending on where you're at. If the layers are farther apart, the hopping is a bit weaker. If the layers are closer together, it's a bit stronger. And this modulates the valence band and conduction band maxima and minima, leading to a spatial periodic potential landscape, which can localize charges in the system into a lattice. And if we'd like to start understanding the many-body physics of the charges that reside in that lattice, we can start with the humble Fermi-Hubbard model, single-band Hubbard model, the simplest Hamiltonian which could describe the physics in the system. So we have 2 terms, a kinetic energy term, which describes intersite hopping with some kinetic energy T, and then an on-site interaction, which is parameterized by U, just a hard shell interaction. And even this simple model already captures some very nice many-body physics. In particular, if I put 1 charge per lattice site, that's a half-filled band. We normally expect that state to be metallic. But of course, if the charges are interacting very strongly with each other, and in particular if they have strong repulsive interactions, meaning that the on-site interaction is large compared to the kinetic energy, it turns out that the energy penalty for 1 charge to hop to the next site, as in conduction, is too large, and instead the charges stay exactly where they are, glued in place. They localize into a gapped charge insulator, a Mott insulator in particular. And of course we can include more and more fancier terms into the Hamiltonian if we start including nearest neighbor or next nearest neighbor interactions, long-range interactions. We can look at things like generalized Wigner crystals, which are essentially very similar to a Mott insulator but spaced out over multiple lattice sites. And of course, there's a lot of very interesting physics in twisted Moiré structures of 2D semiconductors beyond the Hubbard model. So these are some of the most striking examples. So for example, there's superconductivity in twisted bilayer WSE2, unconventional superconductivity. There's a zoo of magnetic states that appear in most of these twisted TMD systems. So for example, there's competition between an anti-ferromagnetic ground state and kinetic magnetism occurring in this pairing of WS2 and MOSE2. And one of the most pivotal discoveries in these systems is probably the recent discovery of a new Hall effect, the fractional quantum anomalous Hall effect, in which the charges fractionalize. But all these have in common is basically that these are correlations among fermionic constituents in the Moire system. None of these have anything to do with bosons. And it turns out that there's a reason why very little work has been done in the direction of studying the many-body physics of bosons in twisted TMD systems. And that's because the fundamental bosons that we have to work with in these semiconductors are excitons, and excitons have a problem. The problem is that they have a short lifetime, usually picoseconds to microseconds, depending on the details of the exciton. And this means that the population is constantly changing in time. They're out of equilibrium. There's usually a spatial gradient and a temporal gradient. And usually they're optically injected, and usually optical injection introduces excess energy, which means they're also out of thermal equilibrium. You have a hot gas of excitons. And finally, excitons are neutral, which means that interactions are generally much weaker than the Coulomb interaction between two bare charges. This you can get around a bit by studying dipolar excitons, where one charge species is localized in one layer and the other charge species is localized in the other layer, giving you a permanent dipole moment. Then you have a nice, strong dipole-dipole interaction, and you can get significant interactions. So dipolar excitons are what we're going to focus on if we want to study many-body physics. So this is the first device architecture that we're going to explore. It's an effective bilayer electron system. It's actually, confusingly, it's made out of 3 layers. But we'll treat this layer as a single layer. So this is a Moire layer made of WS2 and WSE2. And then separated from this by a thin dielectric barrier, about 2 nanometers thick, is a monolayer of WSE2, which forms the second layer of our bilayer electron system. And that's all embedded in a double capacitor structure, which allows us to tune the electric field and the chemical potential of the system. Or alternatively, we can think of it as we can control the charge density in both layers independently. Okay, and so the general recipe for building bosons in the system is as follows. We're going to start with a correlated insulator in the Moire layer, and then we'll apply an electric field to pull some of those charges out of the correlated insulator and into the monolayer. And these will then bind to the hole that they leave behind to form a dipolar exciton. And how do we detect these correlated insulators? We have a really kind of convenient tool using the monolayer as a sensor. So it has a second purpose in this structure as a sensing layer. And we'll exploit the fact that the 2s Rydberg exciton that lives in the monolayer has a relatively small binding energy, and it's rather sensitive to screening. So if I put the 2s exciton in proximity to a metallic state of electrons, it will be screened away. The electron-hole interaction will be too weak for the 2s exciton to bind. On the other hand, if the electrons that are nearby form an incompressible state, like a correlated insulator, for example, then the 2s exciton should still form, should be tightly bound, and we should still see a 2s exciton signal. And what that looks like in practice is this. So this is looking at the 2s exciton resonance in reflection contrast, while tuning the charge density in the Moire layer. So we have a neutral monolayer, and then we have charges in the heterobilayer that's below it, and we monitor what this 2s exciton is doing. We can see at charge neutrality, we have a strong 2s exciton, which then disappears, and then it reemerges at specific gate voltages, specific charge densities. And these very bright reoccurrences, these actually correspond to exactly 1 and 2 electrons per Moire unit cell. So this would be then the Mott insulator, and this would be a Moire band insulator, so filling the first Moire band. And then we also see in between these very bright spots a few weaker reoccurrences of the 2s exciton. These correspond to generalized Wigner crystals, like I mentioned earlier, these sort of long-range patterns which emerge due to next nearest neighbor interactions. Okay, and now we can track what the 2s exciton is doing in the bigger parameter space of the top gate and the bottom gate voltage. So here I'm essentially extracting the strength of the 2s exciton resonance as I vary the bottom gate and the top gate. And down in the bottom right-hand corner, we have the mod insulator that I showed you on the last page. And then as we move along this anti-diagonal, what we're doing is we're increasing the electric field, pulling charges out of the heterobilayer, out of the mod insulator, and putting them into the neighboring monolayer. And as we do this, essentially we're doping the monolayer, and we can see that this is causing the emergence of negative trions in the monolayer. So we indeed have electrons in the monolayer, but at specific gate voltage pairings, for example, right here, at this point, we have the case that the 2s exciton reemerges, signaling that we have an incompressible state, and that the trion simultaneously disappears, meaning that the charges that are in the monolayer are not contributing to the formation of trions because they're bound up into a different state, which is these dipolar excitons. So exactly at these specific gate voltage pairings, we have all the charges in the monolayer behaving like the monolayer is neutral because they're just bound up in a different state. Okay, so what's important here is that this dipolar excitonic insulator state, this is it's a charge incompressible state. This is evident from the fact that the 2s exciton is visible, but it's not exciton incompressible. The interactions between the excitons are rather weak. And so we can simply turn up the electric field a little bit and we'll get another dipole. We can continuously vary the density of dipoles. And the reason why the interactions are weak is simply that half of the exciton is free. So part of it is living in this, the context of the superlattice where it's subject to quenched kinetic energy. The other half is a charge. The electron is a charge living in a free monolayer where it can simply move around. So these excitons are very mobile and the correlations are therefore very weak. And so what we'd like to do to get around this problem is look for a system where we can implement a moire pattern in 2 different layers such that the charges that make up the dipolar exciton are both subject to the exact same moire potential. And this is how we do it. So this is the second system that I'm going to discuss. So it fundamentally comprises of twisted HBN, which is acting as a tunneling barrier, but it's also the source of the superlattice, which I'll come back to in just a second. And then on either side of this, sandwiching it, are a monolayer of WSA2 and MOSA2, and that is again embedded inside of a capacitive structure. So the twisted bilayer HBN near 0 degrees gives rise to a periodic electric polarization, and that's because the different stacking orders across the moire unit cell realize these special points where you have nitrogen and boron atoms sitting directly on top of each other, and within the local unit cell, you have charge transfer, a net charge transfer, which gives you an electric polarization. So across the moire pattern, you have kind of these locales that have no polarization, then upward polarization, then downward polarization, and this repeats, and it projects an electric field into the neighboring monolayer materials, giving them kind of an electrostatic potential. So here the moire potential has an electrostatic origin, and because the moire potential comes from the same spacer that's between these monolayers, they're subject to exactly the same moire potential, just with a minus sign. So there's a mirror plane about the center here, and the moire potential is antisymmetric about that mirror plane. Okay, so before we start looking at the data from the twisted HBN device, I want to show you a control device that has exactly the same architecture, but with a natural bilayer of HBN, so no moire pattern. And MOSA2 and WSA2, when you stack them together, they form a type 2 band alignment, meaning that the conduction band is in the MOSA2 and the valence band of the system is in the WSA2. So if I dope electrons into the system, they'll go to one layer, and if I dope holes into the system, they will go to the other layer. And we can see this from the electrostatic behavior of the excitons. So with electron doping, we have negative MOSA2 trions with neutral WSA2 exciton. And with hole doping of the system, we have a positive WSA2 trion and a neutral MOSA2 exciton. Now, if we look at the device with a twisted HBN, it looks very similar. We have the same general electrostatic behavior, but with one key difference, which is that at discrete gate voltages and discrete lattice filling factors, we have kinks in the trion signals and the neutral excitons. And these, if we back out the density from the gate voltage using a capacitive model, knowing the twist angle of the HBN, these kinks exactly correspond to filling factors of 1 and 2, that is 1 or 2 electrons or holes per lattice site. In other words, we expect that this corresponds to something like a mod insulator and this a band insulator, exactly as we saw in the previous system. More evidence comes for this from our friend, the 2s exciton, but a slight variation of the 2s exciton. So here we're looking at a charged interlayer trion. So there's a 2s exciton on one layer bound to a charge in the other layer. Now the 2s exciton doesn't see very much of a Moiré potential because the electric field that's generating the Moiré potential is mostly out of plane. And the 2s exciton does not couple strongly to an out-of-plane electric field. So this guy is kind of living just in a flat landscape, whereas the charge is living in a periodic potential. And so that's this signal that you see here. This is a neutral 2s exciton. Then when we put charges into the system, we get this 2si minus interlayer trion. And then exactly at a filling factor of 1, we see that there's a discrete kink in the exciton energy. And we see this both in reflection contrast, we see it in photoluminescence very clearly. And by contrast, if we look at the control device where we have no more potential, this kink is gone, but we see the exact same states. And so this, this kink, we believe, is related to the localization of the exciton in the presence of the Mott insulator, which quenches its kinetic energy. Now we can then track that kink as a function of temperature. Up to, let's say, 70 Kelvin, it's still sort of visible. It gets blurrier and broader. And then by 90 Kelvin, certainly, the kink is gone. And we interpret this basically as the melting of that correlated insulator at about 70 Kelvin, which corresponds to a charge gap of about 6 millielectron volts. And for comparison, in the previous system, the Mott insulator melts at around 210 Kelvin, corresponding to about a factor of 3 larger charge gap. And these numbers roughly make sense when you consider that the length scale of our Moiré period in the HPN system is much larger. It's about 12 nanometers versus 8 nanometers. Another important aspect of this system that makes this device architecture very special is that it's sort of reconfigurable. Depending on whether we put the same charge type in both layers or opposite charge types in the 2 layers, we can get different lattice geometries. So if it's the same charge type, whether it's both electrons in the upper and lower layer or both holes in the upper and lower layer, you get a honeycomb lattice where the alternating corners are occupied in opposite layers. This gives you a sort of layer pseudospin texture. On the other hand, if you have opposite charge types in the 2 layers, they kind of co-locate in the same lattice sites, which should promote pairing of the electrons and holes into bosons. Unfortunately, in our device, we're not able to easily control the charge density in the 2 layers separately. The tunneling barrier is a bit too thin, and our gates simply can't inject large densities of electrons and holes in the 2 layers. Nevertheless, we can do optical experiments to inject excitons. So, because we have a type 2 band alignment and the tunneling barrier is thin enough to permit a small amount of tunneling, we can optically excite excitons in one layer. These then break apart, one charge transfers to the other layer, and we form populations of electrons and holes in both layers. So that's evident from the fact that if we look at this photoluminescence as a function of gate voltage, we can see that basically at most points near charge neutrality, we have the coexistence of negatively charged MOSE2 excitons and positively charged WSE2 excitons. And if we keep track of where these excitons are residing in the broader phase space of the back gate and the top gate, we can see that there's a finite region, an extended region in the electrostatic phase diagram where both layers are charged simultaneously, and that's this shaded region here. Strikingly, exactly in this extended region, we see that the 2s exciton is quite visible. And this is odd because we have charges in both layers. We would expect then that the 2s exciton should be screened away, but it's not, indicating that even though these charges are present, they're forming an incompressible state. And we take this as evidence for the presence of dipolar excitons, which don't contribute significantly to screening the 2s exciton. So exactly as in the previous device, we believe that here we have essentially a dipolar excitonic insulator. One last important detail. This is a very nice recent work from the group of Alan MacDonald, is that even though we've so far neglected the in-plane components of the electric polarization, they do play a crucial role in the quantum physics of the system. So this is showing you a sort of cartoon of what the electric field distribution, the in-plane component of the electric field distribution looks like in real space across, let's say, the B lattice site of the Moiré superlattice. You can see that all these polarization vectors kind of swirl around a rotational center. And so this chiral center gives rise to a so-called layer pseudospin skyrmion, because we have these dipolar excitons coupling to both the out-of-plane and in-plane components of the electric field. The layer pseudospin skyrmion is expected to give rise to topological excitonic bands. And it's very possible that the excitonic insulator that we've observed is topological in nature. So with that, I'd like to summarize and conclude. So I showed you two different bilayer electron systems. One is a sort of half Moiré system where we observe for the first time a strongly correlated dipolar excitonic insulator made out of forming spontaneously from electronic order. And in the second, we extend this to a double Moiré system where we perfectly align the Moiré pattern in two different layers of our bilayer electron system. We observe fermionic order and the possibility of a dipolar excitonic insulator, which theory says could be topological in nature. And of course, we'd be very interested in studying exciton-exciton interactions in this system, as well as looking for signs of topology using, say, counterflow drag experiments. And so with that, I'd like to thank all of my collaborators and my students and the members of my team who did this research, and in particular, Emin Ben-Meni, who has performed both of these experiments himself. And of course, our collaborators who are growing our beautiful crystals, and the funding agencies, and all of you for your time and attention.
Thanks a lot for this fantastic talk and telling us about these truly amazing experiments. We have now some time for questions.
Kick it off. Thanks, Nathan, for the excellent talk. I have a quick question regarding the HPN. Like, I think this approach—
The twisted HPN.
The twisted HPN, I think, is pretty smart what you guys are doing. So would that
Not
also
our
work?
idea.
Huh?
Not our idea. Just
I see.
this is a beautiful paper from Wang Yao's group.
I see.
They proposed this idea quite a while ago, and yeah.
Nonetheless, I think the approach is pretty nice. Would it also work with the homobilayers? So here you're using—
Yes.
Yeah.
Yes, exactly. So for realizing this kind of system where we have electrons or holes doped into both layers, it's much easier to do with homobilayer.
And then you can perfectly align them. The lower and the upper layer is quite nice.
You mean angularly aligned?
Yes.
Yes, this is also important to him. So that's an important detail that I left out, is that the angular alignment between our top and bottom semiconductors is close to 0 degrees. And this is to promote interlayer tunneling. It'll be even stronger when the K points are actually aligned.
And the second question, I don't know if this makes a lot of sense, but is there any chance that the dipolar insulator becomes sort of long-range ordered magnetically? Is there any sign, or you guys—
so far in these simple experiments, there's no sign of long-range ordering of the dipoles. This system has a much better chance than the first system for realizing long-range order of the dipoles, because we should have quenched kinetic energy for the dipoles themselves. Magnetic order, I'm sure it's there, because whenever you have all these many body states have magnetic order, it might be weak.
Yeah.
There might be competition between different magnetic ground states, but there is surely interesting spin physics.
That would be interesting, though.
Sure.
Okay.
Yeah, absolutely.
Thanks. That's amazing. Yeah. Thank you.
Any other?
Yes, thank you very much for the talk. I have two questions. The first one is, could you explain why you call your excitons Rydberg excitons? Because in your spectroscopic data, I only see n equal 1 peak and not higher
sorry, I've gone too far.
States, Rydberg states.
Which button do I play? There we go, okay. Good. Yeah, okay, so in these data we see 1s and 2s excitons. In other experiments, we see up to 6s, 7s. Okay. Probably the language is a bit conflicting with the idea of a Rydberg atom, which is a highly excited state. This is the terminology that was kind of adopted by this community, that anything greater than n equals 1 is a Rydberg exciton.
Okay. And the second is more technical about, in order to, as you call it, quench the kinetic energy of the excitons, what kind of trapping depth do you need in terms of energy? Maybe I missed it, but I didn't see any number.
It's hidden a bit in this plot. Typical numbers are tens of millielectron volts. And the bandwidths that you get are a few millielectron volts. Yeah.
Okay, thank you very much.
Mm-hmm.
Any other questions?
Yeah, thanks for the amazing talk. Also, a question to the second part where you have the twisted HBN.
Mm-hmm.
In principle, there's also kind of then some papers on the kind of ferroelectric switching of this.
Mm-hmm.
Do you
Yeah.
see anything close to this? That you see a change when you have like a very high field of this HBN?
No,
lattice?
we haven't been able to do this. It's possible that we're away from a twist angle that allows this kind of physical reconfiguration. I think the nanomechanics of the system have not been very well studied so far, unlike graphene. But it's possible that our stacking angle has the pattern rather locked in, which doesn't allow us to tweak the lattice to reconfigure it.
Yeah,
I think this is happening more in like marginally twisted.
Yeah.
Like
It
closer
would
to
just be
less than 1
interesting
degree.
because you're also quite close to zero, right? At like
Yeah,
1 or 2.
exactly. So this is 1.2 degrees roughly, and I think most of this ferroelectric switching is happening below 1 degree.
Thanks.
Mm-hmm.
This works, right? Yeah. Okay, thanks for this nice talk. I have a probably very naive question, being a chemist perhaps. But when you put when you dope the material, in particular the moire pattern material, don't you get relaxation? Don't you get changes in the bond lengths which then destroy the current moire pattern that you have?
Not much. Not much. Nothing that we can observe. In the end, the charge densities that we introduce they're large compared to, let's say, charge densities that you induce in other semiconductor platforms, but they're not large enough to have significant renormalization effects. So, I think this has been observed a bit in ionic liquid-gated systems where they achieve 10 to the 14 or 10 to the 15 carriers, like 2 orders of magnitude larger than us, but we're still far away from that.
Okay, thanks.
Mm-hmm.
All right, so I think it's time to finish this session. If there are more questions, let's hope that it continues during the coffee break, but let's thank Nathan for this fantastic talk again.